Okay, well, it's wonderful to be here and talk in front of this particular audience, which is to me an unusual audience because you guys know too much. Kind of daunting. It's also nice. Normally, I thank the organizers at this moment for the chance to have an invited talk, but in this case, that would be kind of funny, right? Because I did a self-invitation here. Okay, so today I want to talk about, well, I have a little funny title. You know, this is a ripoff, of course, of Einstein's quote. You know, it would be sufficient to understand an electron. In my case, I'm an experimentalist. This translates into a very small subpart of that I would eventually like to coherently control in time and space an electron. That's one of my big goals that I've set for myself. And let's see. All right, so before I forget, because I sometimes get excited and then I forget to do this, so here it is. There's lots of people involved with different steps of the different things I'm going to talk about. You know, most important for the thing I will focus on today is actually Brett Barwick, who built an important part of the equipment I'm going to talk about, and Adam Caprice, who did some of the theoretical analysis, two of my grad students. And other people that important is Kees Uitwaal. He provided with the laser that we are using, so I should mention him. And of course, on the side I will mention some of the electron matter optics stuff that I picked up a bit from Dave Pritchard and Alex Cronin, who is here. And now our newer stuff is with Ahmed Sewil, so lots of people are involved somehow. All right. So 10 years ago, or 11 years ago now, I started at UNL assistant professor, and what I wanted to do is test the dispersionless nature of the IB effect and see the free fall of electrons. My background is I worked in Zeilinger's group. I had been working on an atom interferometer that together with Marcus Oberthaler we got to work, and this was with Jörg Schmiedmeier and some of the other people. And of course, I had learned about the Colella-Overhauser-Werner experiment, so I thought, gee, it would be wonderful to do electrons because I knew that Fairbanks had done something in the past, and people like Jerry Gabriels and Carl Wyman told me that that was kind of controversial experiment, so I said, hey, wonderful to try to go there experimentally. The other thing that I learned about from Zeilinger is the dispersionless nature of the AB effect, which had never been shown for the original experiment, not the one that you showed us, right? Which is kind of a unique version of that. So that I wanted to do. And of course, if you get excited by that, then you realize what you need is an electron interferometer. So you need to start building one. And the first thing then we did is, so this is kind of the context, so we made a coherent beam splitter to start out with. And that was, we did that by realizing the Kapitza-Dirac effect, which was an old prom defined in 1933, but of course from Dave Pritchard I learned it had been done with atoms, and so we said, can we do it with electrons? Now you need orders more of magnitude of laser intensity, but we finally pulled that off, which was well received, and you can read a review of Modern Physics that came out 3 years ago on lots of the details that I did. So, but we need more electrons. So at some point I invited Dave Pritchard to give a colloquium at our place at Nebraska. And he of course, he saw that I was doing this with a pulsed laser at 50 hertz. So most of the time, all the electrons just went flying by in my coherent beam splitter. Although it was clean, the idea was no material close to the beams, no decoherence or dephasing phenomena, maybe a clean interferometer. That was my goal. But then he said, well, you know, you don't have counts. Why don't you try it with a material grating? So yes, then we stuck in a grating, and of course together with Cronin, who has talked earlier yesterday about this topic. We did that, and of course that works, and you can build interferometers with it. The other thing that we did is at some point I invited Mark Kasevich from Stanford, and he showed that he had made these pulsed electron sources. And I realized that, gee, if I could just trigger the electron source, then with a laser diffract them, but make sure that the laser is pulsed, and that is a high rep rate, so femtoseconds, then the count rate goes up too. So that was the other approach, and we started building a pulsed source. Now that had led to lots of, let's do other things, and one of them I'm going to talk about today. So the grating led to, we realized the Mach-Zehnder interferometer, I won't talk about today much, and it also led, the pulsed source led to a study of the AB effect, which is also published. And so that is what I want to focus on today, and especially what I want to do is show that I really don't understand the problem, regardless of the fact that we made a contribution. So let's start and focus on that particular topic. So let me ask a question. Can you make a spaceship move without any propellant? And of course, the answer should be no, right? Okay, let me try to do this. And this is something that's been stolen from a book that Arne van Roorlich wrote in 2005. So, and we'll discuss this particular thought experiment. So here you have...
You don't have the spaceship that's fall gravitationally towards the Earth.
No, the spaceship is just, you know, out in space with nothing there. No, you can't pull on anything. There's nothing there, right? Yeah. And you can't throw anything out. You can't spit. You can't do anything. Okay, so you're kind of stuck there. Now, on the other hand, now consider this thing. If you have two counter-rotating cylinders that are both charged equally, they have, let's for the sake of the argument say the same radius, although it would be very hard to realize. And you consider a charge that's just sitting here at the side. Now this seems to be an acceptable system that is stable in its own right, because outside here there's no electric field, positive and negative charge, right, equal, and there's no outside no magnetic field because we assume this to be very long, and thus it's kind of like a solenoidal construction. So there are no forces and we're all happy. Now, what then Arne van Roorlich say, add then friction between the two cylinders, what's going to happen? What's going to happen is the magnetic flux here is going to decrease. Maxwell's equations kick in, you get an E field over here, and the E field start accelerating the charge. Good, as soon as that charge, then there is of course force. But then you immediately wonder, wow, this is interesting because this thing started with no net momentum, or so it seems, and here of course this thing seems to gain momentum. What happened with momentum conservation? So there you go, you have indeed, somebody said it, you have an E cross B term. So the E field of the charge acts, if we assume this to be an unshielded cylinder, inside you have a B field, E cross B field, you have a momentum term that changes over time because this thing starts to move. So the E field here changes, and if you work this out, which we've done, you can fully integrate that, then indeed you can show that momentum is conserved. And that seems to be a very, very nice situation. And of course, in general, if you look in Jackson at the back, you find this for momentum conservation, right? Okay, so how can you make a spaceship move without any propellant? So what you do is you take your spaceship and you have your satellite hanging somewhere. They rev up the system for you. They hand it to you. They put it in your spaceship, right? Then you have this revving in your spaceship. You close the door. You, of course, already mounted the charge that is mounted with a rod to the front of your spaceship. Then friction kicks in. And suddenly there's a force in the charge. There's no back action other than in the electromagnetic field, and your spaceship starts to move. So this you could call, if you like, a linear momentum battery. Okay? Good. Now I need to make a big transition. So now I'm going to talk about the Arnold-Bohm effect, because I think ultimately this is related. Now we'll come back to the spaceship at the end, or closer to the end of the talk.
What do the patent office say about that?
I haven't patented that yet. I should. I didn't even think of that yet. Yes. That would be fun. Maybe I didn't check in the literature if actually somebody called that a linear momentum battery. It would be fun to try, actually, just for the heck of it. All right, so here's a picture we made with pulse ray. Here you have a solenoid, and you see the blue lines are the supposedly magnetic field. The green stuff around it is a vector potential. And so we all know, right? We've just seen this extensively. Two paths where a coherent electron beam can just pass by and interfere. We'll eventually here see, if you recombine the beams, a phase shift, which is dependent on the enclosed magnetic flux, or, if you like, the curl of the the ring integral of the vector potential. And of course, yeah, you see, if you think in terms of Lagrangians, then you have a V dot A term. Here the V dot A term, V and A are parallel. Here they're opposed, and thus the phase shift on both sides of the solenoid is opposite. All right? All right, we've all seen that. And of course that was predicted in 1959. This we've seen also before, that of course Chambers did this with a magnetic whisker, and you see that the tilt of the phase shifts getting stronger and stronger as different heights as you enclose more magnetic flux. So that was of course a wonderful experiment, and I think the most quoted one is this famous one by Akira Tamura, who is here, and he showed us about that particular one. So that is all wonderful. Now what is the significance of it? That has been said also in the previous talk. There is no force, but still an effect. And I like this particular quote, a recent one, that it is controversial, the Arno-Bohm effect, in part, and there's probably more reasons than one, because of the modern philosophical aversion expressed by Einstein and others to the concept of action at a distance. Now that's kind of interesting. If you read some books, then you'll say, hey, well, the electron goes to the vector potential, and so we can assign to the vector potential some real meaning. On the other hand, if you look at some of the papers of Aharonov, he more seems to state that what happens is that the magnetic field here can act non-locally at, you know, the position of the electron, if you like, I mean a coordinate in a wave function. Yes? So there may be different views on that, and I think his argument is the vector potential, if you give it, it is overdetermines the system in such a way that the phase shift here is only the term modulo 2 pi. So that seems to be an argument to say, well, I don't need to know the full vector potential, and maybe it's indeed better to say that the B field acts non-locally. But that, of course, leads to that philosophical aversion. All right, now I want to talk about dispersionless, and so before, and I know that there's some experts, but I also know that there's some people from other areas, right, in this group, so I think it may be good to just do this. Let's do something we all know. Let's make a little wave packet, and I'm thinking of a matter wave packet, and of course how you do it, you have different momentum components, right, and then if you put this in a certain shape, and I don't want to give a homework quiz to tell me what shape I should make here to make the pulse, right? Because I'm not as daring as Sam is. So we can make a Gaussian shape here, of course, in momentum space, because the K is momentum. And of course, you see the pulse appear in position space, right? So that is what a pulse would be. Now, of course, we can make that thing propagate, right? So if you have, oh, hang on. If we make this thing start, then of course we just have a wave packet that propagates. I took here one that doesn't fall apart, right? I took conditions that the matter wave didn't broaden much. I didn't want to confuse the issue here. Later on you'll see that.
What's the dispersion relation?
Okay, now that's a good thing. For this one, I really took a linear one, so this is really an optical wave packet. The next one will be one where it's quadratic, where it's a matter wave. So yes. I kind of a rip-off, but just to get the point across. So what can I do to affect this wave packet, right? Because we're talking wave mechanics, we're talking quantum mechanics. What I can do, I can take each component, K, the components I showed you earlier, and quote, make a phase shift for each one of them. So I can add up here a phi of n to each K, and I can just dial them in and see how that wave packet propagation is going to change. So for instance, suppose that I change each wave packet and I give it a linear phase shift. Now, as soon as I do that, you see something interesting how this propagates. You see that the, if I call this the group, in its entirety, propagates in a certain speed, but you do see it is slower than actually the phase propagation, which if I follow one of these individual peaks, right, the phase velocity, it's different. So now you have actually, well, if I would translate this classical physics, this means there would be a delaying force on the group, right? So if there is dispersion on the packet, then there is the equivalent of a force. This is why this dispersionless test of Arno-Bohm effect, I'm explaining the word dispersionless here. Okay, on the other hand, you could have media that don't do this, but do this, that change the phase for each K component in the same fashion. That means that I could factor out the e to the power r phi out of this wave packet and just say, hey, I've multiplied the wave packet with a phase shift, while the propagation of this thing hasn't changed in any way, so there's no force, but you just multiply it with a multiplicative phase, like what we typically mean that happens in the Arno-Bohm effect, the way you see it in the books. Okay? So, how does that work in an interferometric experiment? Here it is actually dispersion relation, so that's quadratic, Alex. So you can run this thing and then you'll see the field is off at the moment, so you can see that the wave packet falls apart, right? And it just keeps on cycling. So this is the idea, is solenoid, these are the two paths associated with an electron interferometer that later on here would be recombined. Now we can turn on a field, hop, and then when you see that one jumped forward and one stayed behind a bit, right? So as soon as I would do something where I actually put a dispersion in here, what would happen is that this thing has a force forward, this is a force backward, and the wave packets would shift. Now I could of course now just say what happens if you change that, when you see that the wave packets, if I go the other direction, they would shift the other way. So this is just the outcome of a very simple, simulation of a one-dimensional quantum mechanical wave packet, okay, that we did. So now that led, oh, hang on. Now, oh, that was with dispersion. So let's do it without dispersion. So what we normally think of the Aharonov-Bohm effect, it is something like this. I run this thing to the end, and the wave packets don't shift back and forth. But what you do see is that the phase within the envelope shifts backward and forward if you ramp up the B field. So that means if you would recombine these two things, that you get an interference phenomenon, right? Because if here the peaks match up, you get constructive interference, etc., etc. Okay, so you've seen the difference between if there's a force and no force, conceptually. Good. So Zeilinger's idea, I think I'm saying that right, I hope I got the history right on that one, is that what you would do is if there is no force and you scan the magnetic flux, or you make it bigger and bigger, you see an interference fringe that extends, but if there would be a force in the way we just talked about, then the interference fringe would die off, and they would die off beyond the wave packet size, or for a CW beam, the coherence length of the wave packet. Yes? Now, because for this particular experiment, if you look at the realization of the Aharonov-Bohm effect, this is typically in the order of 10,000 to 100,000 fringes. And since the phase shifts are here typically a couple of 2 times pi, that means nobody's ever seen this thing trail off, as opposed to the one exception for a neutron interferometer that you did, right? That is an example that dispersionless phenomena do exist, but it hasn't been demonstrated for this one yet. And that, I think, would be wonderful to see.
Many things have been demonstrated with neutrons first.
That's right, and that's, yeah. Yeah, I don't have a neutron reactor. All right, so this has never been done. So how about something simpler, though? This is a thought that occurred to me when I started thinking about this a couple of years ago. Well, you know, okay, if you can do dispersionless stuff, and we're building then, and we have one interferometer and we're trying to make it bigger, it's hard, we're building the technology. But what about just to measure the force in a time delay experiment? You send by electrons by a solenoid and see if there's a delay. Then you directly know if there's a force or not. That's a different way to perhaps approach the same problem. Well, then, as I said, Kasevich came by, and he had a postdoc, Hommelhoff, who built a thing like this. Well, actually, the story is this. I gave an invited talk on the Kapitza-Dirac effect in ITAMP, and Mark Kasevich gave a talk there too. And he came to me and said, "Oh, Herman, I'm going to do something in electron matter optics." I said, "What?" Because this is a smart person who can do a lot of stuff, right? And I hope to corner a little bit of that area, because there's not too many people there in the United States working on that area. So that was wonderful. But then I invited him for a talk in 2003, and he didn't come. In 2004, and he didn't come. In 2005, he finally showed up, and he told me what he did. And immediately we jumped on it to try to do that. And that was Brett Barwick, who is now working with you, Mark. So field emission tip. Pulsed laser, in this case a femtosecond laser. Electrons are pulled out, the E field is pointing this way, and then you just time here with a channeltron. We're now actually working on temporal lensing with Sewell, where you put a second laser here so that the timing could be in the order of femtoseconds, which means the energy resolution associated with it will be really ridiculous. And that's kind of maybe exciting too, as an aside.
The laser is just to see if there's an electron there?
The laser is there to generate an electron. So when the laser is off, so this is a field emission phenomenon. The DC field is not sufficient to pull out the electrons, but then the E field of the laser will be sufficient to pull the electrons out, and you get a little burst. And with pump probe measurements, we published a paper that shows that this is faster than 100 femtoseconds. So a little burst of electrons. Okay, now of course the time resolution determined by this thing, which turns out to be something like 0.3 nanoseconds, right? It was not a channeltron, it was a channel plate we used for the final experiment. Then you pass by a solenoid, and you want to know, is there a delay if you ramp it up? Now, before I show you that data, you know, how big of a force should we be looking for? And to get that, well, remember that idea from Zeilinger. Then you just say, hey, this distance between these two peaks should here be the same as these two peaks to make sure that you have agreement with the experiments that have been done before. Well, here, such a force would give you this type of phase shift. Here, of course, the AB phase shift. Equate the two, and then you know how much displacement you should make in your wave packet, or time delay if you divide by the velocity. So you know how much there should be, right? Now, at that time, of course, I had lots of people to say, well, you know, why do this? Because isn't that extremely unlikely that there's exactly a force in that prom that will give you that delay? I mean, it's just super unlikely, isn't it? Well, I came across a paper from actually Tim Boyer, who has been always kind of holding a little bit controversial point. This is a 2002 paper. And what he did is this. He took an electron and a solenoid and just did a classical calculation where he figured out what the Lorentz force of the electron on the solenoid is. Okay? Well, this thing generates a B field, so you have to integrate over all these little current loops, and you can do that. He did that with a model of stacked magnetic dipoles. We did it with a current. We got exactly the same answer. And the thing is that here is that particular force expression. Now, if you then do the following thing, you say, suppose that this force would back act, not just be here, but back act on the electron, which is a big assumption, but if you would assume so, then that force will give you exactly the displacement that you need to explain the AB effect. So there is such a force in the prom, not necessarily in the right place and not necessarily the only force. Okay? So, but if you have that, at that time when I saw this, I said, whoa, this might be meaningful actually to do the experiment, right? It's not just a simple demonstration. There is a little bit of controversy at least there. So it's not that crazy. So here's what I already said. Here's the vacuum system is this big. It's kind of nice. And then you have some optics around it and a femtosecond laser. And that's about it. So it's actually one of the simpler experiments I've been involved with in my life. Especially because I had an excellent grad student who was working on it. So this is actually looking down the bore. Here you see a little white dot. That is actually the field emission tip illuminated with a laser beam just to make it visible. Here is one of the configurations that we used where you have a little solenoid encapsulated in a metal shield. There is just a yoke to terminate the magnetic flux. And we pass it through it and then we see what happens. Now, the result is effectively this. Here's the timing spectrum of the electrons for a particular setting, different colors, different settings of the magnetic field. Here is the prediction that would be given by that Boyer's force. Okay? This is, of course, the prediction that you find over in the books. There should be delay, and the experiment confirms that. And as far as I know, that was the first time that anybody confirmed that in that configuration there is no force. Okay? Now, of course, if I do show you this, you get a little bit worried if you see here lots of zeros. And, okay, one of the things we did, we measured in situ the induction. So we put around the magnetic yoke, we put a little pickup coil, and as you turn up the magnetic flux, you see a little peak over which the integration is proportional to the magnetic field, and then you step it up more, step it up more, step it up more, step down, step down, step down, so you monitor. So I know that the wires weren't broken inside while doing the experiment, for example. Right?
Let me ask a question.
Yeah.
The experiment is done with, you step the current up and you leave it there?
Yep.
And then you step it up again and leave it there?
Yes.
Step
So,
it up there. Every data point is
yeah.
So that when there's
yes.
no time varying magnetic field.
Absolutely right.
Okay.
So, yeah, so each time spectrum is taken for a fixed value of the current through the solenoid for a fixed magnetic field, and each spectrum here corresponds to that one point that you were talking about, the delay point.
Right. So
that's right.
Know that the next question is, well, what about when it is varying?
I didn't do that. It's interesting in its own right. So, if you want me to do that, I'll do that. Yes?
Yeah, there's a reason for it.
There's a reason for it, good reason.
Okay, I love it. Thank you.
Good
Collaboration. Boom. That's what I wanted for the meeting anyway, right? Okay, you have to tell me about it. I don't know what the reason would be. Otherwise, I would have done it.
See my corn, right?
No, that's not. There would still be no effect.
Right.
He's talking about a force that changes the speed.
Yeah, right.
The actual force in this context changes the momentum.
Yeah. Don't worry. Don't give him the theory, Mike. Just
No,
ask him to do the experiment.
Nothing would happen. No collaboration.
I'll play that game. That's good.
But nothing's supposed to happen.
All right. So now let's look at the electric version of the Harvard-Bohm effect, which was also proposed in 1959, because we did an experiment on that one too now, which we haven't published yet. So there was a paper in PRL 1985 by Mattiuzzi and Pozzi, where if you think of the idea of that you enclose an electric flux and it's supposed to give rise to a phase shift, right, which we know, they were talking about that by replacing the plates that set up the E field with wires, because it's, number one, experimentally more, probably more accessible, and the other reason is that if you look at that PRL, at the end they say this work was stimulated by a remark made by Professor Aronov at a symposium, and he pointed out that the constant phase difference due to a bimetallic wire is a true quantum type 2 non-local phenomenon, which is an interesting statement at the time. So what is the idea there? What do they mean? Well, here is the wire, right? And if I look as a function of location in this direction, and you plot the phase shift accumulated by an electron that passes by, it is flat, and then in between the wires there is a phase change as a function of position, and it's flat again, if you just figure out this particular configuration. Which means, since there's no phase change as a function of position, there is no force that deflects a beam that comes by here to the left or the right. That's kind of what this is about, right? So,
May I ask you,
yeah.
about the dipole moment of this wire? The wires have a clear dipole moment.
Yes, I'm not
range interaction.
That's right. I'm not saying that there is no E field out here. It just turns out that if it's something like this, the interaction drops off here with 1 over r, while the path length over which you are interacting grows with r. So somehow you got to get a balance, and of course you got to be a little bit careful because if you express it in phase, you get logarithmic terms, you have to integrate over that, and then you'll see that the phase shift, regardless of the fact that the E field here drops off, the phase shift is independent of distance. That's the result of that. You actually have to do it to convince yourself, but that's known in literature. It's a known fact. But yes. So here, that's kind of what the type 2 is about, right? I mean, for an experimentalist, that means the particle is plowing through a field, right? While in the original electron magnetic AB effect, you're not plowing through a field. You could make that a little bit finer definition, but I think for this purpose that will suffice. Okay? So what we did is, because that had, then at some point I realized that these zeros are kind of annoying, it would be nice to do one where we show we could actually get some delays, and that would be interesting, because Boyer actually also pointed out, for that particular experiment, that there was supposed to be a force. Let me go back to that. So at this date, people were only considering phases changes in this direction. But since this is on all the time, right, then there are gradients in this direction. So you might get delaying forces. And of course, things were modified in a way that makes sense, and you can also see it in the original paper by Aronov and Bohm. You're supposed to pulse this thing so that the wave packet is contained within the electric field, but it wasn't done at this particular time. So it was interesting for me to actually do this experiment and have 2 wires and have a wave packet passing, or an electron, not wave packet in this case, it's classical, passing by, pull out with the laser beam electrons and see what happens. And here are the 2 wires in the configuration. So you do this, and then you see, indeed, this is the data, so there are delays. We can measure down here delays to clearly 1/10 of a nanosecond. Well, remember, for the magnetic AB, we just needed to see 100 nanoseconds. So we certainly have the accuracy to see stuff like this. Here are delayed pulses coming in. This was Boyer's projection, where there's a slope. And this is actually then a numerical simulation, because we found out that the data curves around the 0, point. So the slope here is perfect, or at least as good as it looks within the noise of the data. And then as you go about, there's some curvature. Now that has to do with, if you don't take an impulse approximation, but you just calculate the full trajectory, you get small deviations. And indeed, that theory that we did, or that calculation we did, lies kind of nice on the data. It's not bad. So at this point, these 2 together, I think, make the point that some things that in literature were claimed to be AB effects are, and some, are actually not. And so, and some are type 1 and some are type 2, and there's some mixed. We also propose another one, New Journal of Physics, the Ponner-Motive AB effect. And so I think Herman and Bohm effects are kind of tricky, right? That I think is maybe fair to say, and there's still a lot of debate on that. Now, the paper that we did on the AB, we did a paper together with Akira Tonomura, who is here, which is I'm very happy with. And there were some media things that said something. Here is one from phys.org.web that says, proving an aspect of the AB effect when Newton's third law doesn't work. And of course, it's funny that that seems to be a thing that most people don't like if you say that. As a matter of fact, but if I think here in terms of F12 equals minus F21, right? I don't think there's a problem. It's not right, of course. Why is it not right? Let me start coming back to what I started out my discussion with. Well, remember that Boyer said an electron exerts a force on the solenoid, and he assumed that there's a back action of the solenoid on the electron. So, and I said that is a big assumption. So this is all within this question about what about total momentum conservation, because that's the real issue. I need momentum conservation, period. We all need that, right? Maybe not Newton's third law, but we need momentum conservation. So then we decided, since, and I will tell you that I still don't fully comprehend all of this, but we started analyzing this, and this is a small part of work, about 3 years of theory stuff. We tried to distill this down to the simplest problem we can think of that had all the elements in it. That, the one that we found was this one. If you think of this solenoid being made out of charged particles that move, and then you can just two charged particles, here one moving this direction, here one that moves that direction, you get actually something you find in the Feynman lectures of physics. And there, indeed, the point is made that this particle, if there's a charged particle, it sets up no B field over here, because it's on axis, but this one sets a B field over there. All right? So in other words, on this one there's a magnetic Lorentz force, and this one there's not. And again, you have this problem that one pushes on one and not on the other, just like actually we have here, which kind of illustrates that Boyer's assumption that this thing back acts might be wrong. Okay? So, I'm sorry?
2 minutes.
Oh, that's great.
I like to have questions.
Yeah, no, that's good. That's good. Okay, let's go. So we analyzed this. Yes, it's imbalanced, but we found something that was interesting. We did this at that time because we're kind of deep in the problem. We try to do everything coherently, and so we're also working with electric fields. Now, this Feynman doesn't say, but the electric field is also imbalanced, right? If these move, these are contracted. This imbalance in force is identical in magnitude to the magnetic one, because we actually also got a factor 2 if you calculate E cross B appropriately, the momentum in the field, you need this to put in. So that is our, and then we published that and was picked up in Wolfram demonstration project as a little flash movie.